Welcome to the APL Quest. See APL Wiki for details. Today's quest is the first from the 2015 round of the APL problem-solving competition. We are given two character vectors and are to check whether or not these are anagrams. Here's a simple test case. What we need to do is we want to compare these two character vectors to see if they're the same, but we want to ignore a lot of aspects of the character vectors. We want to ignore capitalisation, punctuation, and spacing. In other words, we just want to look at the actual letters that are present. Let's start to do so by filtering the letters. So we want the letters where those letters are members of the alphabet, but they can be members of uppercase alphabet or lowercase alphabet. So we want to do this membership case insensitively. Finally, we also want to case fold these letters so that we can compare the ones from the two different character vectors. But we can observe that filtering by a membership, that's actually the definition of intersection. So we can substitute this phrase with the case-insensitive intersection and give us the same result. Now we need to put these letters into some given universal order, so that if we do so with two letters that are scrambles of each other, shuffles of each other, so sets of letters, so to say, then they end up being the same order and we can compare them. So one order is the sort order. That works fairly well. So if we call these the letters and then we index the letters by their grade, that gives us a sort of them. And we get the same thing on X. And so we can define a function with this definition, but it's not enough, of course, to just do this normalization. We want to compare them. So we want to compare the two arguments pre-processed by this normalization. X and Y are now considered the same. They are anagrams of each other. And this might well be the shortest solution that we can come up with. However, it does have some issues that we can have a look at. For example, grading can be a rather expensive operation, while sorting can be done faster. In order to get the fastest sort, we want to use one of the idioms for sorting. So here's an example of that. We can see it gets colored differently because we are going to use the fast algorithm for sorting. So this works as well. Furthermore, if there's a lot of punctuation, then we are case folding the punctuation in order to look at the intersection with the alphabet, when it wasn't actually necessary to case fold that. So we could look at the intersection first and only case fold afterwards. For that purpose, we would have to look at intersection with both the uppercase and lowercase letters. And we could do that by taking these are the lowercase letters and then putting the uppercase letters before that. And finally, notice that we are computing this total alphabet of letters every time we run the function. If you were to run the function multiple times, then it's kind of wasteful to compute that alphabet. So we might want to do that once and for all. One way to do that is using a tacit definition. So by changing this brace here into a parenthesis, now it's a tacit function. And we have to modify a little bit what's inside here. So we don't want to mention the argument, it's tacit, but we can take this constructed alphabet and tie it as an argument, right argument, to the intersection. So this is one monadic function that's being applied. Then we have another monadic function being applied and a third monadic function being applied. We can't do three monadic functions in a row like this, but if we compose these two together, then it will be just fine. So this should save us a little bit of work if we're using the function many times. Let's give it a try and see how they stack up against each other. So supposedly A, B, C, D, this should become faster and faster if I've done the thinking correctly. Okay, let's start by constructing some large test case here. We can start off with letters, the alphabet, and let's both have some uppercase and lowercase letters. So if we concatenate the alphabet to its lowercase, then we get this. So these are all the letters. Then we can put in some punctuation. And that gives us this. Then we're going to have a lot of that. Let's do 1,000 characters from that. So this just repeats them over and over again. But we also want to shuffle them around and we want to add some spaces as well. So we can do that with a little function. So we want to take the argument and add some spaces around. So we can just overtake it by, let's say we add 20% spaces on the length. And then we might want to round that off so that we don't end up with fractional characters. This would allow us to change this to a number that would cause trouble. So this just gives us a bunch of non-spaces with a bunch of spaces afterwards. So now we can make a proper anagram of those by shuffling them. So we take the argument and then we take all the indices but in any order of its length on T. And let's create something that's not an anagram of it, and we'll do that by putting in a dash, which is not something we had before, at the first position in T. So now they are not anagrams of each other. Copy in CMPX from the defense workspace for the timing comparison. And then let's construct the expressions that we are going to use. So we want to compare, we want to run these functions a lot of times because that was one of the things that the D was a benefit over C. So we can start off by saying we have 1,000 copies cyclically of TA and TB. So these are the anagrams and the not anagrams. We want to run on each of these, and then we want to have the functions A, B, C, D and concatenated to the entirety of those. That gives us these expressions here. And then we want as left argument, and we want a constant. So we can say we're binding T as left argument to each of these. That gives us these 4 expressions here. And then we can run CMPX on that. And it will take a little while. But if I have done my thinking correctly, then we should get progressively better and better performance. And that's indeed what we did get. So we can see that we got some speed ups more and more. However, and here's the thing. An anagram is not so obviously just looking at the letters. It's actually overdefined in the problem specification. It says using all of the letters, and it also says ignoring spacing, capitalization, and punctuation. Could have said using only the letters, or it could have said just an anagram of a string and ignores word spacing, capitalization, and punctuation. So there's actually some freedom to interpret this whichever way we want. For that, let's have some more interesting examples. Here, I'm using some letters that are not, so in the first two character vectors here, there's some letters that are not in the just plain Latin uppercase and lowercase alphabet. As well as writing with some punctuation here. But the important part is that I'm adding digits. And digits are not letters, so we could say that they shouldn't be included because they're not letters. But if you're only removing spacing and punctuation and capitalization, you can't say that digits are spacing, you can't say that they're punctuation, and they're certainly not capitalization either. So it could be either one of these, in either one of these definitions of it. So how can we do this? Right. Um, there are a lot of characters out there, and we don't want to write a list of all of the characters that have different properties. Luckily, Unicode does define a whole table of properties for every character. And we can hook into those kind of sneakily by using quad R or quad S because they allow PCRE or Perl style regexes, including character properties, and those are exactly the Unicode properties. So what we can do here is we can say, and it's nice to state it in the negative because we want to not we can't really extract the letters as much as we can easily remove letters. So we are going to remove letters from U, and we can remove any character that does not have the property of being a letter. So the uppercase P here means the opposite. A normal lowercase p is having the property of being a letter. But here we're removing things. We want to keep the ones that are letters. So we are removing anything that is not with the property of being a letter. And we can do the same thing for B, of course. So we can see that both the punctuation and digits are considered not letters, but the special characters that are not in the Latin alphabet, those are still considered letters and they're being kept. And we can incorporate this into a function similar to what we had before. So we want comparison over and then some pre-processing. So we start off with the sorting idiom, and then we want to case fold so that we are case insensitive. But instead of doing the intersection, we are now keeping this function here, which is just extracting anything that's the letters and removing everything that is non-letters. So that's one way of understanding it, and we can try this. Oops, sorry, we should have an each here. So what we can see is that the first two, they're obviously different because they're using different letters. The next two, removing the punctuation and capitalization, then they are considered the same, even though they are using letters that are not in the Latin alphabet. And then we have the two that are using digits. Both of them are considered anagrams of each other. So the first one is pretty obvious. The 1, 2, 3, 3, 2, 1. The order doesn't matter. Percent and minus are considered punctuation. Second one are entirely different digits, and that's because we have removed all the non-letters, and all digits are not letters, and therefore there's nothing remaining. Even the dot goes away because as punctuation, we're comparing two empty character vectors to each other, and then they're considered the same. But we can also define it the other way, where we are not interested actually in what's a letter and what's not a letter. Rather, we are looking at what is at removing certain types of characters. So we want to remove characters of a certain class. There are multiple things. We want to remove any character that has the property of being a mark. And so this is like a spacing mark, things that adjust the spacing. So that's part of being spaces. We want to remove anything that has a property of being a space in itself, of course. And then we want to remove anything that has the property of being punctuation. Punctuation. And we can look at what happens when, well, we should before we run this, we should really take this and try it out. So here we can see that we kept all the digits, for example. And now we can try it. And now we can see that the last one, so let's look at U and V again. The last ones are considered different from each other because we now keep the digits, even though the punctuation has been removed. And I think that's all there is to say about this problem. Thank you for watching.